This balloon is an s orbital, okay, which means it's a perfect sphere. I just can't make a perfect sphere with a balloon, okay, but let's just pretend. So if I orient this balloon different ways, if it's a perfect sphere, does it really change anything? No. So all S rooms, all S sublevels only have one orientation because they're all perfect circles, which is why all of our S rooms have one bunk bed, and this is a bunk bed, okay? Or they only have one orbital. A p orbital, on the other hand, does anyone remember what the p orbitals look like?
Like 2 sections of each other.
Yeah, so like 2 on top of each other. Some people say like a infinity or a figure 8 sign. Okay? Alright, so our p orbitals here, okay, look like this. Okay? This can be oriented in 3 different ways. If you think mathematically, it can be along the y-axis, the x-axis, or the z-axis. Okay? So 3 orbitals exist in a p subshell.
What about like diagonal or something?
So here's why there can't be any like diagonal ones, is because when these all connect, because there's like 3 bunk beds or 3 orbitals, this is what a p orbital looks like all together. You have 1, 2, and then 3. And there's no room for any more because these are all electronic. They're all negative, right? And so they don't really want to be by each other in the first place. Okay? Everyone kind of see that? All right, and then so all p's have 3 bunk beds. The d orbitals, I'm not tricky enough to make balloons for these ones, but these are the 5 different d orientations, which is why d rooms have 5 bunk beds. And do you guys see the pattern here? 1, 3, 5, 7, right? So they just count up by 2. Yeah. And then the F ones, I think here's a picture of those are the D's, but I'll show you a picture of the F ones. They get even more because you have 7 different orientations. Okay? Okay, so let's have we filled this chart out yet? No? Okay. So when L equals 0, what type of room am I in?
S.
An S room. Good, Brock. So remember that when L equals 0, I'm in an S room. Okay? The mathematical equation for the range of M sub L is negative L to positive L. That's the range that they can be. So if L equals 0, what does M sub L equal? 0, because it's 0 to 0, which is just 0. Which means there's only one way it can be oriented, which is why we just have 1 bunk bed or 1 orbital. Okay? When L equals 1, what room am I in?
P.
So I'm in a P room now. Okay? So now our values will range from -1 to +1. So then if you write out all the numbers in that range, that gives us -1, 0, and 1, which is why you have 3 bunk beds in the P room, or 3 orbitals. Okay? Then, all right, so then this one would range from, so now we're going from -2 to +2, which has 5 different ones. Because you get -2, -1, 0, 1, and 2. And then our F's range from -3 to +3, which is how we get 7. Okay? So one thing that's important to recognize, it doesn't matter if I'm on the 2nd floor or the 4th floor. In the 2P room or the 4P room, if it's P, it's always 3 bunk beds. What does the number in front signify?
Energy level.
Just the energy level or floor, right? Don't think you have to do math and be like, there's 4 Ps. 4P just means the 4th energy level in a P sublevel. Yeah, Mitchell.
So why do they have to be bunk beds?
We'll get to that here in a second. Ooh, ready? Let's do this. Smiley face question, okay? Don't say it out loud, but just show me on your fingers how many electrons do you think can sleep in the 3s room? Just show me on your fingers how many electrons do you think can sleep in a 3s room? Don't be shy. How many electrons do you think can sleep in a 3s room? All right, Morgan, why do you think 2? Yeah, because how many bunk beds are in 3s? One bunk bed. All S rooms have 1 bunk bed and 2 electrons can sleep. So the reason why they're bunk beds is that electrons don't share beds. They're all negative. They don't want to share. And so it always has to be a bunk bed in the end. Good. If you were holding up bunny ears, you can have smack.
Yes. Yes. I'm the fastest, but I just want smiley faces.
Okay, so with our 3rd and 4th quantum number,
I would need 2,000 smiley faces.
okay? Something you need to understand here, everyone, is that all of these, so this represents the entire P room, all the balloons together, okay? And the electrons can change between bunk beds all they want. They can move from the top to the bottom, they can trade partners here, and we don't know the difference, okay? So that's why from the periodic table, we can't tell M sub S. We can only tell N and L, because we don't know the difference, okay? Because they all have that same energy between the bunk beds in the same room. As long as they're in the same room, they can trade beds all they want. Yeah,
So does it
Jason.
matter what energy level they are? They'll have the same amount of electrons, no matter what, at the same energy level.
So say that one more time.
So for 4s and 3s and 2s and 1s, they'll all just have 2 electrons.
Yes. So if it's an S-type orbital, it's always just 2 electrons. How many would all the p orbitals hold? 6. Yep, exactly. Doesn't matter which floor we're on, it still only holds that many. Okay, so our last quantum number now, it goes to final quantum number that we'll get to. First off, look at this pattern, okay? So N is our energy level, okay? N squared would actually tell us the number of orbitals per energy level. Or in our analogy sake, you could say the total number of bunk beds on that floor. So look at this pattern, ready? So N equals 1. 1 squared is 1, which is why there's only 1 bunk bed on the first floor. 2 squared is 4, because there's 1 bunk bed here, 3 here, it adds up to 4. Same thing here. There's 1 bunk bed here, 3 here, 5 there, and it adds up to 9, which is 3 squared. So there's kind of a nice pattern where if you square N, you can see the total number of orbitals available on each floor. Okay, ready? So now tell me this. Smiley face. Just think in your head. How many then, what's the max number of electrons that can stay on the second ring or the second floor? Just think to yourself, what's the max number of electrons? Question, Mitchell?
Yeah, I have a question. So like, we always like, alright, like learn that like there's 2 on the first level and then 8 on the, like what is that kind of the same thing?
Yes. So tell me this. So how many can stay on the second floor?
2.
4.
Oh, 4.
On the second floor, how many electrons are there?
8.
Why is there 8? Because there's 4 bunk beds, which each hold 2 electrons.
Oh, so there's up.
So there's 18 on the third.
So the
one,
max amount you can hold on the second ring is 8.
and the max on the third would be 18. Right?
Yes, the third ring could hold a max of 18 electrons. Yeah, in the end. Does everyone see that? So yeah, this is how we learn why in this model, why there's only 2 beads on the first ring. And there's only 8 beads. I think I lost a bead. There's only 7. Oh, or they did it wrong. 1 and 2. We'll pretend we lost one. But that's why there's only 8 on the second. And that's, I like how Mitchell put it too, that's the max number. It doesn't have to be full, but that's the max it can hold. If you were thinking 8, go ahead and have a smiley face. Okay, so our last quantum number, the last piece to our hotel, is we want to know what floor they're on. We want to know what room they're in. Okay, focus back in front. We want to know the bunk beds, and then we want to know if they're on the top or the bottom bunk. Okay? Because that's as specific as we can get here. So this is known as the spin quantum number, m sub s, and it can be one of 2 values. The electron is either on the top bunk or on the bottom bunk. Spin up or spin down is what we call it. And the values are plus 1/2 and minus 1/2. Those are like the numerical values for them. Okay, it's important to recognize that an orbital can hold 2 electrons and they always have opposite spins. So you can only put 2 electrons on a bunk bed and they're never going to share the bottom and they're never going to share their top. They always have to be opposite each other. Yeah, Austin.
So the orbitals are each like a balloon, pretty much?
Yes. Well, it depends on what orbital you're talking about, I guess.
Like the P one.
So in the P, let me switch some of these around. I should have gotten the same colors. So if you look at the 2 red balloons, these 2 together are actually 1 orbital, right? But then this would be top, like up spin and down spin. Does that make sense? And then like the blue and the green are another orbital, pink and yellow. So that's how you get 1, 2, 3.
And then you can only have 2 in each one of those orbitals?
Yeah, so between these 2, only 2 electrons can exist. Right, great question. Okay, so when we talk about the spin, right, you can kind of think of it like the Earth a little bit if you want. How the Earth orbits the sun, but at the same time the Earth is also rotating. Right, and that's how our little electrons are as well. Is they orbit the nucleus, but then the electrons themselves are spinning. And they always spin opposite ways. Okay, so our last thing with our quantum numbers, okay, so just like with m sub L, with m sub S, the spins are with the same amount of energy. Okay, so electrons, they'll never both be on the top, they'll never both be on the bottom, but they could trade if they wanted to, and we can't tell the difference. So that's why really after today, we're mostly going to be focused on N and L. I want you to know what m sub L and m sub S tell us, but you can't tell me on the periodic table what those values are, because in terms of energy, they're exactly the same. Okay, so then the next thing we're going to transition into is understanding that there are rules that our hotel follows in order when it fills itself up. Okay, the first main rule that the hotel uses, or the atom uses, is known as the Pauli exclusion principle, which tells us that no 2 electrons in an atom can have the same 4 quantum numbers. Okay, so in an atom, no electrons can be exactly the same. They could be on the same floor, they could be in the same room, they could be even on the same bunk bed, but this is what tells us they'll never both be on the top or they'll never both be on the bottom, because otherwise they'd be exactly the same. Okay, so here's our overview. What does the principal quantum number tell us? The what? Good, the energy level. Yep, principal quantum number is the energy level. Azimuthal quantum number tells us the sublevel, very good, or the shape of it, right? That's our S, P, D, or F. Our third quantum number tells us the orbitals, or the bunk beds within it. And then our spin is down to the exact electron now. Yep, very good. So notice that we get, this is like their address, right? It's a little bit overwhelming.
What's their address? What's
So next time we're going to learn how to write the address.
Gotcha.
Okay, thanks.
But now we know the address is telling us.